Hey there, Math 141. Welcome to episode 5 of Math 141 Summer 2020 Recitation. Today we are going to be going to infinity and beyond, as the famous Buzz Lightyear would say. In particular, in section 2.6, we're going to look at limits involving infinity. And in section 3.1, we're going to do some problems regarding tangents and the derivative at a point. Okay, so limits were kind of the first big calculus idea, which we learned in chapter 2, in which we're wrapping up today. Although they're going to stay with us for the rest of the semester. And then the derivative is the next idea, which is going to become super important as we continue here in Calculus 1. Okay, so let's get into it. Before we do any problems today, I want to make one thing abundantly clear. I'm sure this was mentioned to you before, but I want to re-emphasize it here. Infinity is not a number. Okay, infinity itself is not a number, it's really an idea. This is a way, so infinity is a way of describing behavior, as things get arbitrarily large in magnitude. As things get arbitrarily large in magnitude. Okay, so it is not a number. Like we can't officially plug infinity into an equation or something like that. Really what this is a way of describing things. So as what this is saying, when we talk about, say, the limit as x goes to infinity of f of x, before we would plug in x equals whatever our limit, whatever the limiting value was, into our function. But what we're going to see here is that we can't technically do that because infinity doesn't make sense as a number. Okay, really this is just saying as x gets really, 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 really big, what is the tendency of f of x? What is happening to f of x? So I just wanted to mention that before we get started. I think that's an idea which many people in mathematics find difficult. Or maybe they just aren't taught it properly whenever they first learn about infinity. So I just figured that I would mention it to reinforce that notion. But let's get started with some problems here. The first problem, which I would like to do from the homework, is problem 4. And in problem 4, we will be finding such limits as x approaches infinity. Find the limit of f of x, I'll write that, f of x equals minus 5 plus 8 over x over 2 minus 6 over x squared as x approaches infinity. I'm going to write that just x arrow infinity because I'm lazy. And as x approaches negative infinity. Okay, so these are the two limits which we're asked to compute here. We'll start with the limit as x approaches positive infinity. Okay, so as x approaches positive infinity, we want the limit of negative 5 plus 8 over x over 2 minus 6 over x squared. Now there is one very big idea, there are several ideas which are important. One very big idea is going to be important here, and that is the following fact. So let me put it in a little box here. For any constant, I'll call it a here, the limit as x goes to infinity of a over x equals 0. Okay? So for any constant, the limit as x goes to infinity of a over x, that's just 0. I hope this kind of makes some intuitive sense. As x gets really, 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 really big, as the denominator gets huge, this fraction as a whole is going to get tiny. For example, if a is, say, 2, just as an example, well, then this thing is going to be like, as x gets bigger, it's going to go from like 2 over 10, 2 over 100, 2 over 1,000, 2 over 10,000, and it's just going to get tinier and tinier and tinier. And so basically it becomes 0. It never officially becomes 0, again, because we can't plug infinity in, but basically it gets super, super close to 0. So that's the idea which we're going to use here. And in particular, we're going to use some of our very nice limit laws. So I can actually, I can write this limit as, okay, there we go. I can write this as the limit as x goes to infinity of -5 plus 8 over x over the limit as x goes to infinity of 2 minus 6 over x squared. Okay, and so now if I want, and you don't have to show all of these steps, I'm going to show a little bit more steps than maybe you need. Maybe some of you need to see all the steps, some of you don't, but just so that everybody, I hope that this way everybody can follow along. I'm going to do it very deliberately. So now, because limits work very nicely, we can add them, right? We can split up this numerator limit into its 2 separate pieces. And similarly in the denominator, let me draw a line here to make it clear where we are dividing things, where we're going to a new line. So I can break up the bottom part as well, minus limit as x goes to infinity, 6 over x squared. Okay, and now we get to use the fact which we pointed out a moment ago. So for any constant a, the limit as x approaches infinity of a over x, that's just going to be 0, which means in particular that this limit as x approaches infinity of 8 over x is going to be 0. Well, and this one down here is technically 6 over x squared, but that's also going to go to 0 for the same reasoning. Which means that this is just, well, the limit as x approaches infinity of -5 is just -5. And similarly, the limit as x approaches infinity of 2 is just 2. And so this fraction comes out to just be -5 over 2. And there we go. We've got ourselves an answer. Okay, so first we looked at the limit as x approaches positive infinity, and for that we used this identity that for any constant a, the limit as x approaches infinity of a over x is 0. We then use that to observe that these 8 over x pieces, this 8 over x piece and the 6 over x squared piece, those guys really don't matter in the big picture. I'm sorry, guys, because they go to 0 as x goes to infinity. So really we can just look at these first terms, the -5 and the 2, and look at that fraction. The second limit will follow a very similar procedure. So now we're looking at the limit as x approaches negative infinity. And again, our fraction is going to be -5 plus 8 over x. All of that over 2 minus 6 over x squared. All right, so now we're looking at the limit as x approaches minus infinity. Well, we're going to do basically the same thing. I'm not going to write out all the steps this time. I am going to point out basically the same fact. Actually, let me just go back up to our previous fact. Let me not even make it a new box here. If I change this to say as x approaches plus or minus infinity in our little box here about the limit as x approaches infinity, if I change this to a minus infinity, it is still true that the limit as x approaches minus infinity of a over x is 0. Okay? Again, if we think about an example, if I look at, say, 2 a equals 2. Well, if I look at if I look at 2 over negative 10, 2 over negative 100, 2 over negative 1,000, I'm still getting closer and closer to 0. This time I'm just approaching from the negative side instead of the positive side. But in either case, the destination of 0 is the same. And so from that, actually, we can immediately see that this 8 over x, this is going to go to 0. And so is the 6 over x squared. This is also going to go to 0. And so this is just negative 5 over 2. Again, basically the exact same work that we would have done a moment ago. Or rather, that we did do a moment ago. So yeah. So this was a case where the limit as we approach positive and negative infinity was the same, and that's nice. Okay. So that is our first problem of the video. Feeling good on a roll here. Let's jump into the second problem, which is going to be the next one, I believe. Yeah, we're going to go straight to problem 5 now. And problem 5, we are going to, this is a tricky one. Find the limit, and the limit which we are given is the limit as x goes to infinity of sine 2x, 20x over 10x. Okay, so we want to find this limit. Well, if I just plug in as x goes to infinity, so as x goes to infinity, sine of 20x, well, sine of 20x just keeps on, if I look at the graph, sine of 20x just keeps on going like, it just keeps on going up and down and up and down and oscillating periodically until forever, right? Ad nauseum. Right, so sine of 20x, it doesn't really, as we approach infinity, it doesn't really settle down, right? It never settles down. It's always kind of jumping up and down like this. And so the limit as x approaches infinity of just sine of 20x, that is, excuse me, it's not equal to 0. Why did I say that? It does not exist. Right, because it keeps on going up and down and up and down. And so it never settles down. So sine of 20x does not exist, that limit. But that does not mean that our current limit, sine as x approaches infinity, sine of 20x over 10x, that doesn't necessarily mean that our current limit does not exist. And here is the important observation, which is going to guide us toward successfully finding a solution here. I don't know much about sine of 20x as x goes off to infinity. Like, I know it's going to keep on going up and down like this, but like, I don't know specific values of sine. We know a few of them, right? Like I know sine of pi over 2, sine of pi over 3, but I certainly don't know all of the values of sine. But I do know that sine of 20x is going to be between -1 and +1 for all x, right? We know this to be true. This is true for sine of x, and so sine of 20x, it's still certainly true. Okay, if it was 20 sine of x, that would be a little bit different. Then we would be between -20 and +20. But with the 20 on the inside here, it is still true that sine is going to live between -1 and +1. Well, since that is true, that means that if I divide everything here by 10x, that -1 over 10x is going to be less than or equal to sine of 20x over 10x, and that is less than or equal to 1 over 10x. Right, all that I did was I took the inequality we wrote just a second ago and I divided everything by 10x. That's totally legal. And now is where we're going to make another observation. Well, notice that the limit as x goes to infinity of negative 1 over 10x, well, that is 0. This is basically the same idea that we talked about a moment ago, right? As x gets huge, 10x is going to get huge, and so negative 1 over 10x is going to get tiny. Okay, and for the exact same reasoning, if I approach infinity, then 1 over 10x is also going to go to 0. So do you see where this is going? So now I can say by the Sandwich Theorem, Sandwich Theorem says that the limit as x goes to infinity of minus 1 over 10x is going to be less than or equal to the limit as x goes to infinity of sine 20x over 10x. And am I going to fit it in here? Limit as x goes to infinity, 1 over 10x. Well, this is the same as 0, right? We just found that these two limits on the left and right here are 0. So 0 is less than or equal to the limit as x goes to infinity, sine 20x over 10x, which is less than or equal to 0. So surely we must conclude that the limit as x approaches infinity of sine 20x over 10x equals 0. Okay? So one important takeaway from this is that the limit of our numerator, so we have this fraction here, sine of 20x over 10x, the limit of the numerator did not exist. However, that did not mean that the limit of our entire fraction did not exist. Okay, that's important. It's a very important observation. And you see this kind of thing a lot with trig functions. The other trick here is that we use the Sandwich Theorem. Okay, we noticed that sine was bounded by these two functions, by these two values, negative 1 and 1. And those gave us some functions which we could more easily take the limit of. Then we were able to apply Sandwich Theorem to take us home. Now, another important thing which I want to highlight here is that we cannot, this kind of looked like one of those problems where we were going to use the relation limit as x approaches 0 of sine theta over theta equals 1. We cannot use that here because we are not taking the limit as x goes to 0, right? We're taking the limit as x goes to infinity. This value is important here. Okay, the fact that we're taking the limit as x approaches something different means that we cannot do that. So be careful, because I could totally see on a quiz or an exam, I'll admit whenever I looked at this problem, my first thought was, oh, this looks a lot like that identity. However, we have to pay close attention and make sure that we are taking the right limits. Okay, so that's just a little thing to be cautious of there. Okay, so that gives us the first two problems of the day. Let us next jump to problem 11. Okay, there were no requests for this class. These are all my own selections. Problem 11 says find the limit, and the limit we're given is x approaches infinity, root x to the 4th plus 3 over 5x squared plus 4. Okay. So how are we going to go about this? Well, I want to make a note here, and we're going to solve it in a slightly different way, but I want to make an intuitive observation which might help guide your thinking. So the intuitive observation is the following, and again, we'll solve this rigorously in a second, but this might help guide you. I know this helps guide me. Well, as x goes off to infinity, x to the 4th plus 3, well, that's basically just x to the 4th. Like, if you look at these two things, whenever we shoot off to infinity, this plus 3 here, it doesn't really make a big difference as we get bigger and bigger. So that means that x to the 4th plus 3, the square root of that, is basically the same. So I'll put like double squiggles here for approximately. This is basically the same as just square root of x to the 4th, right? Because x to the 4th plus 3 is basically going to be x to the 4th. And the square root of x to the 4th, well, that's just x squared. And this is nice, because then if we look at the limit as x goes to infinity of x squared over 5x squared plus 3, well, we can factor out an x squared. And I'm going to go through this kind of quickly again, because we'll do this problem in detail in a second. 5 plus 3, oh, I forgot my limit. I'll write that in real quick. Limit as x goes to infinity. Okay. And this limit here is just 1/5, because 3 over x squared goes to 0 as x goes to infinity. All right, so this isn't a super formal way of doing it, I admit, but this is my intuitive understanding of how I think about this. This is nice because then, whenever we go through and do it, the rigorous way, using all the right steps, and not approximating like this, we can see if our answer matches up. Is our answer close to 1/5, or is it something totally different? If it's something totally different, maybe we've gone awry somewhere. So I wanted to point that out just to kind of demonstrate how I think about these problems. And I think that as we progress throughout the semester, you'll develop more of that intuition as well. But let's go ahead and look at this thing as it is and look at it for real. What I'm going to do, so my numerator, I've got this root x to the 4th plus 3. And a nice little technique, which I hope you've seen either in Mackenzie's video or in the textbook, or perhaps you've done it in your own work here. Well, if I factor out the highest power of x from that, then I have plus 3 over x to the 4th in my numerator. Okay, so my numerator, under the radical, I factored an x to the 4th out. Similarly, my denominator, I'm going to factor out an x squared, because that is my highest power in the denominator. Okay, so now you can see the denominator. All that I did was factor an x squared out. Okay. And now, my next observation, well, I can pull the x to the 4th out from under the radical, but when it comes out, it becomes x squared. That is because 1 plus 3 over x to the 4th. That is because we're pulling out the square root of x to the 4th, which is x squared. And in my denominator, I have x squared, 5 plus 4 over x squared. Now, I hope that you're excited because, yay, we get to cancel out some x squareds now. That is super nice. And we're left with the limit as x approaches infinity of root 1 plus 3 over x to the fourth. This would be an x to the fourth over 5 plus 4 over x squared. Okay, now from here, well, 4 over x squared, that's going to go to 0 as x goes to infinity. And 3 over x to the fourth, that's going to go to 0 as x goes to infinity. So this is really just root 1 over 5. And most people like to write that as 1/5. And sure enough, it matches up with kind of our intuitive thought process. So, in this problem, we use this trick where we factor out the highest power of x in both the numerator and the denominator. That is helpful because then you can cancel some stuff out a lot of times, and you are oftentimes left with things that are going to go away as you take limits when x goes to infinity. Okay, my computer just restarted, so I couldn't see the problems for a few minutes, so I had to pause the video. So if it seems like there's like a disconnection there for a second, that's why. Okay, let us next do problem 21. Okay, and this is finding, so we're going to find the horizontal and vertical, not horizontal, the horizontal and vertical asymptotes. Vertical asymptotes of this function, which is f of x equals x plus 4 over x plus 2. Okay, now let me remind you for a second how we go about these things. So the line y equals b is a horizontal asymptote of f of x if the limit as x approaches plus infinity or minus infinity is equal to b. Okay, so that is how we go about finding horizontal asymptotes. Why don't we start with that in this case? So in this case, what we want to look at then is we want to look at the limit as, we'll look at both. As x approaches positive infinity, we'll also look at negative infinity in a moment, of x plus 4 over x plus 2. Well, we're going to use the same trick we used a minute ago, where we're going to factor out the highest power of x in both the numerator and the denominator. In the numerator, this comes out that we have x times 1 plus 4 over x. And in the denominator, we similarly have x times 1 plus 2 over x. Okay, well, as we've seen previously in this video, as x approaches infinity, 4 over x is going to go to 0, and 2 over x is similarly going to go to 0, which means, oh, and similarly, additionally, the other thing we can do here is cancel out these x's. And so this really just becomes the limit as x approaches positive infinity of 1. That's all that's left over is these 1's here. Right, these guys are all that's left. And that, of course, comes out to just be 1 because it's just a constant. So what does this tell us? This tells us then that the line y equals 1 is a horizontal asymptote. Horizontal asymptote And if we look at the graph and kind of what this would look like, I have no idea what it's going to look like elsewhere. I'm sure we could figure it out, but the point that I want to demonstrate here is that as we approach infinity here on the as x approaches infinity, this is 1 for y here, well then my graph is going to look something like this maybe. And it's going to get closer and closer to 1, but it's never actually going to hit this line. It might be coming up from the bottom. Again, I don't know off the top of my head, but basically it's going to look something like this. It's getting closer and closer to the line y equals 1 as we go further and further in the x direction. Well, we could also have a different horizontal asymptote as if we look at the limit as x approaches negative infinity. However, in this case, we see that if we follow the exact same procedure that we did up here, everything is still going to work the same, right? We'll still cancel the x's out on our second step. We will still, the 4 over x and 2 over x will still go to 0, even if x is approaching negative infinity. And so we'll still just have that the limit is equal to 1. And so this doesn't give us any new information. And it does tell us, I shouldn't say that, because it does tell us that as we, oh my gosh, that is a very crooked line. It does tell us that as we go toward negative infinity, we're also getting closer and closer to this line. So again, maybe this is coming up from the bottom. I'm not entirely sure off the top of my head, but we do know that it's going to approach this line y equals 1 from either the top or the bottom. Okay, so it does give us more information. However, it doesn't give us a new asymptote because we already had y equals 1 as a horizontal asymptote. So as it turns out, y equals 1 is the only horizontal asymptote of this graph. Okay? Like I said, it is possible for you to have two different asymptotes, one in each direction, but in this case, this is what we find. Okay, let us jump down and look at now the vertical asymptotes. So let me remind you what a vertical asymptote, how those work. So the line x equals a is a vertical asymptote if the limit as x approaches a from the positive side of f of x is plus or minus infinity, or maybe the limit as we approach from the negative side of a of f of x gives us plus or minus infinity. It doesn't matter which one, which plus or minus infinity, nor does it matter which side we approach a that gives us the problem. I shouldn't say the problem, but that gives us this limit. Either any one of these will get the job done. So in this case, we want to know, so for what values of x, does the limit as, actually let me change this variable. Let me say for what values of a does the limit as x approaches a from the plus of x plus 4 over x plus 2 equal plus or minus infinity, or x approaches a from the minus side of x plus 4 over x plus 2 equal plus or minus infinity. So where is this the case? Okay. Well, what we notice is that as x approaches, so as x approaches negative 2, we'll say from the positive side, but really it doesn't matter. X plus 2 is going to go to 0. Right? Like if x is like negative 1.9, and then we look at negative 1.99, negative 1.999, those things are getting closer and closer to 0. In fact, this limit, so really what I'm saying here, is the limit as x approaches minus 2 from the positive side. Actually, I don't even need the positive side, so I'm not even going to put that there. That limit as x approaches negative 2 of x plus 2 equals 0. And this we can see just by plugging in x equals negative 2. Well, that means that the denominator is getting smaller and smaller. Right? Our denominator is x plus 2. So as x approaches negative 2, x plus 2 goes to 0, and x plus 4, well, that just goes to 2. Right? Because negative 4 plus 2, or negative 2 plus 4, rather, just gives us 2. So, as x goes to negative 2, I see that my fraction here is getting closer and closer to 2 over 0. Well, 2 over 0, technically 2 over 0 doesn't make sense. But if I look at, say, 2 over 0.1, 2 over 0.01, 2 over 0.001, and so on, this goes to infinity, because as my denominator gets smaller and smaller, my numerator stays the same, so my denominator, so the whole fraction is getting smaller, bigger. The entire fraction is getting bigger because I am dividing by something smaller. So what we see is that the limit as x approaches minus 2, of x plus 4 over x plus 2 is going to be infinity. And this tells us then that we have a horizontal, we have a, this time a vertical asymptote at x equals minus 2. Okay, now I should be careful as I look at this. So as x approaches negative 2 from the positive side, okay, let me write it this way. So as x approaches negative 2 from the positive side, let me throw that in here, then this limit goes to infinity because my denominators here, these are what my denominators will be as I'm approaching from the positive side. And you can see my denominators will be positive. So all of these fractions will be positive. However, if I look at the limit as x approaches negative 2 from the negative side, well, then what I'm really looking at is I'm looking at, say, 2 over negative 0.1, 2 over negative 0.01, and so on. And so this limit actually goes to negative infinity. Okay, so I apologize. I do need to be careful whenever I'm writing this. Writing the limit as x approaches negative 2, it does matter which side we're approaching from. So we do need to be careful of that. But in either case, we still get this vertical asymptote at x equals negative 2. And so that gives us our vertical asymptote. Again, you can certainly have more than one vertical asymptote, but in this case, we do only have one. So to recap, to find horizontal asymptotes, we look at what happens as x goes to infinity and negative infinity. To find our horizontal asymptotes, we look at the x values for which the limit as we approach those x values is plus or minus infinity. So if you look at a graph of this, our function here at x equals -2, our function, as we approach it from the positive side, we're shooting off to infinity. And as we approach it, again, I don't know what's happening over here. As I approach it from the negative side, I am approaching negative infinity. And so actually we can kind of use all of the information to put together a nice picture, because we also know that as we approach positive infinity, we are approaching the line y equals 1. So it's going to look something like this. And same thing as we approach negative infinity. So actually we know that it's going to look something like this maybe. Yeah. But imagine that I drew it better. So yeah, that's a cool looking graph. Okay. Well, that about does it for 21. 22 is fairly similar, but a bit more complicated. So here at 22, we again are going to find the horizontal, vertical, and this time we're also going to find the oblique asymptotes of, so f of x here, f of x equals 14x squared over x minus 2. Okay, so we'll save the oblique asymptotes for last. Let's go ahead and first, well actually what we should do, yeah, why don't we do this first? So the first thing that we're going to do is long division. Okay, so the reason that we're going to do that is we see that the degree of the numerator is greater than the degree of the denominator. So when I say degree, what we mean is, so this is the degree of the numerator. Degree of the numerator is 2. And the degree of the denominator, well, there's an imaginary 1 here. And that gives us the degree of the denominator equals 1. So I have a degree 2 polynomial, 14x squared, over a degree 1 polynomial, x minus 2, which means that we want to do what's called long division. Okay, so I hope that you remember long division of polynomials. If not, certainly something to review before the exam. So we have 14x squared, x minus 2. It works basically the same way as long division of numbers, which I imagine you've done at some point. So the first thing that we ask ourselves is, how many times does x go into 14x squared? Well, that answer is 14x. In other words, what do I multiply by x to get x squared? So this 14x came from what times x equals 14x squared. Okay, and that is 14x. So now what we're going to do is we're going to multiply the 14x by x minus 2. So that gives me 14x squared, and then minus 2 times 14x, so minus 28x. Then we're going to subtract all of this from 14x squared while we cooked it up. So 14x squared minus 14x squared, that's 0. That should always happen. And then I have minus of minus 28x. That's going to give me plus 28x. Okay. So now the next step, we're going to repeat what we did originally. So I'm going to ask myself, how many times does x go into 28x? In other words, what times x gives me 28x? The answer there is 28. So I add 28 up top. And just like before, I'm going to multiply that 28 by x minus 2. So that's going to give me 28x and then minus 56. then I'm going to subtract that whole thing. So plus 28x minus 28x is 0. And then minus a minus 56 is plus 56. Okay, now we ask ourselves, how many times does x go into 56? Well, it doesn't, because there's no power of x. So 56 then is our remainder. So this is our remainder. Okay, again, the reason that we're done with the long division at this point is that 56 doesn't have any powers of x, but x minus 2 does have a power of x. So this tells me, what this tells me is that 14x squared over x minus 2 is equal to 14x plus 28. Okay, so this is the solution that we got up top. And then for my remainder, I divide my remainder by x minus 2, by what I was dividing by. Okay, so that's where the remainder goes. Again, it might be helpful to think about how we do long division with numbers, and you can see that it's a very similar process. Okay, so now if we look at what we want, okay, so we wanted to find the horizontal, vertical, and oblique asymptotes. And rather than looking at 14x squared over x minus 2, we can look at this other version, which we've now written, because these two are equal. So as you'll recall, for the horizontal asymptotes, I want to look at the limit as x approaches infinity. So that's going to be limit as x approaches infinity of 14x plus 28 plus 56 over x minus 2. Well, as x goes to infinity, the 56 over x minus 2, he goes to 0. But 14x goes off to infinity, right? Because this thing, as x gets huge, 14x is also going to get huge. So this limit is equal to infinity. Going back to the very beginning of this video, since infinity is not a real number, this does not give us a vertical asymptote. Does not give us an asymptote here. Did I say vertical? I meant horizontal. Okay, similarly, if we look at the other limit, the limit as x goes to negative infinity, well, the exact same thing happens. 56 over x minus 2. And that the 56 over x minus 2 goes to 0. And now 14x, rather than going to positive infinity, goes to negative infinity. And for the same reason, this does not give us this also doesn't give us an asymptote. So we conclude no horizontal asymptotes. Okay, remember, a horizontal asymptote would have shown up if we got a limit here that made like a real number as a limit here, but we did not. Okay, so since neither of those gave us a real limit, we see that there's no horizontal asymptote. So now let's look at vertical asymptote. And so there, the question is, for what real numbers I'm emphasizing real numbers here. For what real numbers A does the limit as x approaches A from the left of f of x equal plus or minus infinity, or the limit as x approaches A from the left. I think I said left before. I meant to say the right. X equals plus or minus infinity. The reason I'm emphasizing real numbers here is that, well, we just saw that as x approaches plus or minus infinity, we get that the limit of f of x is infinity. However, that doesn't work. We need it to be a real number, and infinity is not a real number, nor is minus infinity. Okay? Well, if we look at our function here I'm going to look at our original function, where 14x squared over x minus 2. Well, this is going to go to 0, so this goes to plus or minus infinity. So this goes to plus or minus infinity if the denominator goes to 0. If the denominator goes to 0. That goes back to the same reasoning which we used in the previous problem, where we saw that as our denominator got smaller, the fraction as a whole shot off to infinity. And as our fraction got smaller from the negative side, it shot off toward negative infinity. So really, what I want to ask here is for what values of a, does the denominator equal 0? That's going to be where we want to start. In this case, we have that our denominator was x minus 2. And so we see that x minus 2 equals 0 is the same as x equals 2. So we see that the a that we were searching for is 2. And indeed, if I look at, so if as x approaches 2 from the, we'll say from the positive side, well, I have 14x squared over x minus 2 is going to look, well, 14x squared, so that's going to give me 56 in my numerator. If I plug in x equals 2, 56. Okay, that's if I just plug in x equals 2. And so this is going to, so this is going to look like 56 over 0.1, 56 over 0.01, and so it's going to blow up off to infinity. And similarly, if we approached it from the left, the negative side, then we would, as we approach it from the negative side, we would approach negative infinity. So this means that we have a vertical asymptote at x equals 2. Okay. There are no other x values for which our denominator will be problematic, for which our denominator will be 0. And so that is the lone vertical asymptote. Now we need to look at the oblique asymptotes. And these are a bit trickier. I shouldn't say they're trickier. They might be a bit trickier to conceptualize, but they're actually not so bad to find. So the oblique asymptotes, these are basically asking, as x goes off to infinity, what line does f of x get really close to? Does f of x get close to? Okay, well, for this, we're going to use our rewritten version of f of x, where we said f of x was equal to 14x plus 28 plus 56 over x minus 2. 14x plus 28 plus 56 over x minus 2. And so if we take the limit of that as x goes off to infinity of 14x plus 28 plus 56 over x minus 2, well, 56 over x minus 2 goes to 0. So this is getting closer and closer. This is really just the limit as x approaches infinity of 14x plus 28. And this right here gives us the line that we're looking for. Right? As x goes to infinity, This 56 over x minus 2 part, this basically doesn't matter because it's basically going to be 0. And so our function is going to get really, really close to the line 14x plus 28. So y equals 14x plus 28, that should be a 28, is the oblique asymptote. Oblique asymptote. All right. Okay. So oblique asymptotes, what you want to do is you want to, that's where using this long division, which we did up here, really comes in handy. Because that's what gave us this 14x plus 28 plus 56 over x minus 2, which is what led us to our oblique asymptote. All right, let's keep rolling. There are 2 more problems, which I will cover here. The first of which is problem 24. And this says, find the slope of the curve. So the curve at x equals 6, and the curve is y equals 1 over x minus 4. All right, so the way that we want to do this is we want to look at, this is where we start getting into the notion of a derivative. We want to look at the limit as h approaches 0 of, okay, so it's going to be here, I'm just gonna write it in words first. So we're gonna plug in 6 plus h into our function because of this x equals 6. We're gonna plug that into our function minus what we get if we just plug in 6 all over, it turns out to just be h, all over h. This is a limit which we are interested in, and that will give us our slope. So let's go ahead and start plugging stuff in. So this comes out to the limit as h approaches 0. Well, okay, if I plug in 6 plus h, then this is going to be 1 over 6 plus h minus 4 minus, okay, now if I plug in 6, I just get 1 over 2, right? 1 over 6 minus 4, that's 1 over 2. And then my denominator is still just h. Okay, well, let's see what we can do here to rewrite this. The first thing that I see, so let's rewrite our first part. So that's going to be 1 over 2 plus h. Yeah, 1 over 2 plus h minus 1 over 2 all over h. Well, if I just plug in h equals 0 at this point, then I'm going to be dividing by 0. So that doesn't quite work. I'm going to have, yeah, that's not going to quite get the job done. So why don't we do this? In my numerator, why don't we get a common denominator? And so to do that, limit as h goes to 0. So my common denominator is going to need to be 2 plus h times 2. Okay, and let me see. So on top, I'm going to have 2 minus, and then I'm going to just have 2 plus h. 2 minus parentheses 2 plus h. Yeah, okay. That looks good, over h. So all I did in my numerator was get a common denominator. Com denom. Okay. So now, let me see how I can rewrite this. Well, I've got a 2 minus 2 in the numerator up there. So in my numerator up there, I'm left with just minus h over, and then if I multiply this out, that'll give me 4 plus 2h all over h, right? Okay, well, let me see here. So what I can do now is I can bring this 4 plus 2h to the denominator, and I just get the limit as h goes to 0 of minus h over h times 4 plus 2h. All I did here was a bit of algebra. And this, now I can cancel out these h's, and I'm left with negative 1. Oh, I forgot to write limit. Equals the limit as h goes to 0. I'm canceling off those h's, and so I just have negative 1 over 4 plus 2h. And now, if I just plug in h equals 0, all is well. And I'm just going to finish with negative 1 over 4. Plug in h equals 0, the 2h goes away. And so I get negative 1/4 as my answer. Okay? So again, really all that we did here was we used this limit formula. This is the general formula, which you're going to want to get familiar with. Okay, the reason that we plugged in 6 here was just because that was this particular x value we were interested in. You plug in whatever x value you were interested in. You plug that value in plus h, and then you solve, you do some algebra, and you take the limit as h goes to 0. And then you get your solution. All right, that brings us to the final problem, which I am going to do in this video. And that is problem 31. 31 and 32 are similar. I thought about doing both, but I decided just to do 31 and leave 32 for you. If you know how to do 31, then I think you should be in pretty good shape for 32. But of course, please ask if you would like to see that one as well at some point. And this is a bit of a word problem. At t seconds after liftoff, the height of a rocket, is, the formula is 2t squared feet. So then the question is, how fast is the rocket climbing? 5 seconds after the liftoff. 5 seconds after liftoff. And we're told that our answer should be in feet per second. Okay, so we're given the formula for the height of the rocket, and then we want to find the velocity of the rocket, right? That's speed, in other words. Right, fast, so this would be velocity. How fast is the rocket climbing 5 seconds after velocity? 5 seconds after liftoff. I'm sorry, I'm tired. I need to... Okay. So, what we notice here is that, well, velocity, or speed, however you want to say it, I guess I'll say velocity because that's what I wrote here. Velocity is change in position over change in time. In position in this case is height, right? How high has it gotten over a change in time. And so this is really just going to be just like the previous problem, where we are going to look at the limit. So this is just a rate of change, right? So the limit as h goes to 0 of position at time t equals 5 plus h minus the position at t equals 5 over the change in time, which in this case is just h, because it's 5 plus h minus h. Right, this is just 5 plus h minus h. Or 5 plus h minus 5. It's h minus 5. All right? So if we go back and we look at the formula that we used here, it's the exact same idea. And this is how we're going to calculate rates of change in general. So let's go ahead and solve now. Limit as h goes to 0. Okay, so the position, or the height rather, maybe I should have used the word height here. The height at time t equals 5 plus h is going to be given by plugging 5 plus h into our formula 2t squared. So this is going to be 2, and then t is going to be 5 plus h squared minus the position at t equals 5, so minus 2 times just 5 squared all over h. And then from here, it's just going to be taking limits and a little bit of algebra, which we have gotten familiar with. So let's see, this numerator, let's multiply out that 5 plus h squared first. That's going to give me 25 plus 10h plus h squared minus 2 times 25 is 50 over h. And that is the limit as h goes to 0 of, okay, let's multiply that out now. 50 plus 20h plus 2h squared minus 50 all over h. Wouldn't you know, 50 minus 50, so those guys cancel. I also have h's all over the place. H is wild. And so I can cancel some of those out and be left with limit as h goes to 50. H goes to 0, goodness, of 20 plus 2h, and that is just 20 by plugging in h equals 0. Okay. So really the answer, 20 feet per second. And yeah. So again, these rate of change problems, you're going to use this same notion, the same kind of formula here. And this is going to be super important as we continue studying the derivative. We've started looking at it now, but we're going to dive much deeper into it. And that will be probably, the derivative is probably the most important idea. When I think of calculus 1, derivative is what I think of. I think of taking derivatives. So we're going to get very familiar with this formula, and we'll develop some nice tricks pretty soon, which will allow us to do these kind of computations even more quickly. But that is it for today's video. Tomorrow will be a review for your first exam, okay? So please, please, please send me questions that you want to see. I would make sure that you are able to do all of the homework problems on your own without any notes. I think that if you can do all the homework and quiz problems, then you should be in very good shape for the exam. So let me know how I can help between now and then, and